Hello everyone. So in this video, I'm going to explain you mutual exclusion with busy waiting. So in previous 2 to 3 video, we have seen what is race condition, what is critical section, what is mutual exclusion and how to resolve its problem. And there are total 4 conditions that any solution it should satisfy. Okay. So let's see this solution to the problem of mutual exclusion with busy waiting. Okay. So this all are the solution that include busy waiting. Okay, disabling interrupt rate, shared lock variables, strict alteration, test and set lock instruction, exchange instruction, and the last one and very important, that is Peterson's solution. It is frequently being asked in GTU exam. Okay, so some of them I will cover in this lecture, and rest of them I will make new video. Okay, the first one is disabling interrupts. Okay, so you can see over here in this diagram, that is process A, process B, and so T1, T3 and T4, it's the timeline. Okay, and this darkened blue bar is your critical region. That means it is the portion which is shared. Okay, so process A is accessing actually shared resource, so it represent that. So this solution is provide mutual exclusion with busy waiting. So what does it mean, busy waiting? That means whenever certain process is in critical section, the remaining process or the process that wants to enter into critical section, it has to be check or polling on particular condition, particular situation to occur. Okay, so it is just constantly checking whether this condition is true or not true or not true or not. If it is true, then only it can enters into the critical section. So okay, let's see. So you can see in this while loop, condition is always true. Okay, so in this brackets, disable interrupt. So what does it mean? If condition is true, then you have to disable the interrupt. So when you disable the interrupt, that means whatever the process is currently running, it cannot be interrupted by other external event or external signal or arrival of any new processes. Okay, so you can see whenever process A enters into the critical section at time T1, okay, so disable interrupt instruction is executed and it is turned off. After that, it enters into the critical section, and once it completes its task in critical section, that means whatever the resource this process A wants to access is now done, then again you have to turn on the interrupt, that means enable interrupts. Okay, and after that, that is your reminder section, that means non-shareable portion of particular process. Okay, so this is the solution provided by disabling interrupt solution. But there are various disadvantage, or I can say it is not efficient way. It is unwise to give user process the power to turn off the interrupt, because when we turn off the interrupt, that means this particular process cannot be interrupted by any external event. So sometimes it may cause your system to crash down. Okay, so it is not effective way. If one of them did disable interrupt and never turn them enable interrupt again, then it could be a end of the system, and same for the vice versa. If the system is a multiprocessor with 2 or more CPUs, disabling interrupt affect only the CPU that execute the disable instruction. The other ones will continue running and can access the shared memory. Okay, so it's just a solution, but it is not it is unattractive. Okay, so there are other solutions. Let's see that. So next one is a shared lock variable. So shared lock is having a value 0 or 1. Okay, so just assume that it's a kind of a variable, and value of that particular variable can be 0 or 1. Okay, before entering into a critical region, process check a shared variable lock's value. So for example, there are two or more processes. If they want to enters into critical section, first of all they will check the value of this shared lock variable. Okay, if the value of lock is 0, then it's set to 1 before entering the critical section and enters into critical section, and once it completes its task it sets it to 0 immediately after leaving the critical section. So what is the scenario? Like if you want to go in the critical region, first check the value of lock variable. If it is 0, that means critical section is not occupied by any process. Okay, so there is no one, so let's just go to there. So just process think that, and before going into the critical section, it just update the value of lock variable with 1. So what does it mean? Whenever value of this variable is 1, that means critical section is occupied by some process. Okay, so when it is already executed by a particular process, and at that time let's say process B arrive, so again it will check the condition, and what is the value of shared lock variable right now? That is 1. So this particular process, it will wait until its value become 0. If the value of lock is 1, just I have said, it wait until it becomes 0 by some other process which is in critical section. Okay, so let's see this algorithm. While true, set shared variable to 1. So what does it mean? It is right now 0, and if it wants to enter into critical section, it's set to 1. Okay, so you can see the process A enters into the critical section and it has sets lock's value to the 1. After that, it just perform whatever this process wants to do with shared resource. Okay, so right now it is in critical section, and after that, once it has completed its work, it set the shared variable to the 0. Okay, and after that reminder section. So just like that, any process, it can enters into the critical section by checking the value. Now, what is the problem in shared lock variable? If process P0 sees the value of lock variable 0, okay, and before it can set it to 1, context switch occur. So it has checked the condition. Oh, there is no other process in critical section. Okay, so it is just going to critical section, but before it modify to 1, context switch occur. Okay, so now process P1 run and find value of variable lock 0, so it sets value to 1 and enters into the critical region. Now process P1 value of this lock has not been updated by process P0 due to context switch. Okay, and after that P1 comes, and again it sees the value of lock variable as 0. So if it obviously if value is 0, that means there is no one in critical region. Okay, no one is competing for that. So okay, no one is there. Okay, let me go into that. So this particular process goes into the critical section and change its value to 1. Now what happened at some point of time, P0 resumes and set the value of lock variable to 1 and enter critical region. Boom. What happened? In the critical section right now there are 2 processes at the same time. Okay, that means this solution does not provide mutual exclusion. Okay, so this condition, the most important condition, is violated in this approach, so it is not also welcomed at that way. So after that, test and set lock instruction that comes into the picture, and let's see what does this it provides. So TSL resistor lock, it is kind of a machine level instruction. Okay, test and set resistor lock. So it read the content of memory word lock into the resistor Rx and then store a non-zero value at memory address lock. So what this instruction do? It reads the content of memory into resistor Rx and then store the non-zero value at the memory address lock. The operation of reading the word and storing into it is guaranteed to be invisible. No another processor can access the memory word until the instruction is finished. CPU executing the TSL instruction lock the memory bus to prohibit other CPUs from accessing memory until it is done. Okay. After that, test and set log instruction. So over here, let's see example of this, how it's work. Okay. So enter region. So it is referring to before entering its critical region, process calls enter region. So if I want to enter into critical section, so enter region, in the critical region, and exit critical region. Okay, just like that. So inside this enter region, what you need to perform to access the critical section? TSL register lock, copy lock variable to register set lock to 1. Okay, so what will happen over here? This is the entry of this critical section. So lock will become 1. You can see previously value is 0. Okay, and value of this lock is copied into register. So you can see value of this log is copied into this register, so it's 0. Okay, and after that this lock is set to 1. Okay, after that what is comparison? This register with 0. So was lock variable is 0 or not? That means they are performing comparison operation. Okay, so if it was non-zero, then lock was set, and so loop. Okay, jump not equal to. So if it is not equals to 0, that means both the value are different. That means 0 is not 0. Okay, then enter into region. If it was non-zero, then lock was set, and so loop. After that, return to the caller. That means critical region entered. After that, leave region. When the process wants to leave critical region, it calls leave region. Okay, it's very easy. You are just copied value from lock to register and setting the lock variable, comparing value using this CMP instruction. Okay, it's same like a lock instruction, lock variable value. It is like that same, but over here you are just using machine instruction. Okay, so when you leave a region, when you want to leave region, okay, you can see this is the exit of this critical section. So what you are going to do, move 0 to the lock. That means store the 0 in lock variable. So lock is set with 0, and return to the caller. Okay, after that let's see exchange instruction. So enter region. What is the code for entering into region? So over here you move register with value 1. So what does it mean? Put 1 in the register. After that, exchange swap the content of register and lock variable. Okay, so for example, let's say right now lock value is 0 and register's value is 1, and after exchange what will be value of this register is 0. Okay, now compare the register value with 0. Was lock variable 0? That means if this comparison is true, that means value of this register is 0 and this is match. Okay, so comparison is yes, value is satisfied. Okay, so jump not equals to enter region. Okay, if it was non-zero, that means if condition is true, that means it's non-zero. Okay, lock was set, and so loop. Return to the caller, critical region entered, and leave the region. When process want to leave the critical region, it calls leave region. So what you need to do whenever you want to leave the region, move lock 0. That means 0 is stored into the lock variable. After that, return to the caller. Okay, so this all are the, I can say, not these all are the solution, but it is not that effective, and also they are not being asked in GTU question, okay, GTU exam paper. So but you should know this. So in next two video I will explain you this reculturation and Peterson solution, which is very 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 important to you will get you will have fun also, and it is also important in GTU exam. Okay, so I hope you understood it. Thanks for watching. Bye bye.